Thank you very much, Vinod, and thank you all for being here so late on Friday. And I know that the title seems far too obscure, which is what I realized rather recently. But hopefully, I explain a bit of why we think this is interesting. Yeah, so I'm from Madras, and those of you who don't know about it, it used to be called Madras. Now it is Chennai, and it's about 300 odd kilometers east of here, in the neighboring state of Tamil Nadu. Okay, so what I'm going to talk about, I'm going to give a brief introduction. It will be rather elementary. I hope that those of you who are here, I mean, excuse those of you who, I apologize to those of you who already know most of it. And then I'll talk about typical entanglement and quantum chaos, and entanglement transitions in coupled chaotic systems, which is the heart of the work. And this work is done with these four people. So what I'm going to talk about is partly based on work with Shashi Srivastava, who's in BECC, Kolkata, also part of the Department of Atomic Energy, Stephen Tomsovic at Washington State University Pullman, Arndt Baker and Roland Kaczmarek, both at TU Dresden, where much of this work was initiated. All right, so just as a background, I understand that this is, see that, I mean, there is a wide spectrum of work in this conference, and let me just introduce some of the basic notions about what I mean by integrable. So the canonical definition of integrability in classical mechanics is simply that if you have as many constants of motion as the number of degrees of freedom, then the system is integrable. So just to give examples via these simple models of particle moving freely within these 2D billiards. Here are three examples of systems with 2 degrees of freedom, because it's just x and y, but also with two constants of motion, energy, angular momentum, the two velocity squares, and then here the product of the angular momentum about the two foci. So there are some rather peculiar symmetries in these problems, which makes this additional constant of motion apart from energy, makes them integrable. Here are orbits which have suffered 100 reflections. It's a single orbit, suffered 100 reflections from the surface, from the boundary rather. And one can see that they form, they kind of lie on regions which are not ergodically filling the inside of this cavity. Whereas if we break symmetries, such as in this case, by combining these two in what's called a Sinai billiard, then it's a completely chaotic system. This is again 100 reflections of a single trajectory. It's filling this rather ergodically. This is the Sinai billiard. This is the Yurimovich billiard, which is or the famous stadium billiard, which is also just a square or a rectangle with two of its ends connected by semicircles. It's again fully ergodic. This is another distortion of the circle, a continuous distortion. So 1 plus cos phi. So this is the cardioid billiard, again a fully chaotic system. So these are integrable, completely chaotic systems. But most of the systems in nature, I mean, Hamiltonian dynamics is actually neither like that nor like fully integrable, neither fully chaotic, but they have parts of phase space which are associated with regular orbits or stable orbits, and those which are not. So here is the same distortion of the circle, but not with 1 plus cos phi the cardioid, but 1 plus 0.3 cos phi, so the Lima zone billiards. So it almost looks like a circle, but in fact, here is the surface of section, which consists of a distance along. So whenever a trajectory hits the boundary, we mark where it hits the boundary, that's this axis, and at what angle it hits this. So the cosine of that angle, which is this, which is essentially the momentum. So this is Poincare surface of section, and one sees that that if we start with this orbit right at the center here, it's actually a periodic orbit, and it's stable, as you can see in some orbit nearby that, remains nearby that orbit. Here is another example of a stable orbit. But if you take any orbit here in this blue region, it seems to fill almost ergodically this particular area. And these are all unstable orbits. So these are all unstable orbits here, and these are stable orbits. So that's the kind of generic phase space picture in a Hamiltonian system. And when we quantize this and we look at the Schrodinger operator with vanishing boundary conditions on these boundaries, that's studying eigenfunctions of quantized chaotic systems of this kind. Then we find marked differences between integrable systems. So this is 100th excitation, 1000th excitation, etc. So the eigenfunctions of this integrable circular billiard, some of these, and the same excitations for the cardioid billiard. And one can see the kind of structures which are there in this cardioid billiard eigenfunction. So what is plotted here is just modulus psi squared. So it's the modulus of the wave function, the position representation, and the intensities of this are almost uniformly spread. There are these fine structures in this, and the study of these, so the kind of the great differences between eigenfunctions in this and this account for a variety of things, whether there is, thermalization and so on in such systems, and in the condensed matter literature, there has been a fair amount of work on the so-called eigenfunction thermalization hypothesis. Basically assumes states which are having some very strong ergodic characters like this, and asserts that subsystems of such systems in some many-body state of this kind is like a typical thermal state. Now, all this is really for single particles. What I'm interested in is having a couple of such particles, each of which is having a range of possible classical dynamics, quantize it, and to look at essentially information theoretic characterizations, especially in this talk. I'm just going to talk about entanglement, and entanglement in pure states, and really entanglement only in eigenstates of whatever operators I'm going to be talking about. This is an experiment which deals with objects which were much discussed here. So this consists of, let me just read out, this is a paper dealing with ergodic dynamics and thermalization in an isolated quantum system. So we demonstrate ergodic dynamics in small quantum systems consisting of only 3 superconducting qubits. The qubits undergo a sequence of rotations and interactions, and we measure the evolution of the density matrix. Maps of the entanglement entropy show that the full system can act like a reservoir for individual qubits, increasing their entropy through entanglement. So this is a 3-qubit transmon system in which they implement this Hamiltonian, which has been studied for many, many years in the quantum chaos literature, which consists of a single spin in which there is a rotation, jy, which alone will just constitute a simple rotation. All the complexity is coming from this pulse where there is a torsion. So there is actually a rotation which depends on Jz, if you wish. So there's a nonlinear rotation or torsion, which is here. And it is, so this is a single large system, but it can be viewed as a collection of spin half particles, and that these are collective spin degrees of freedom. So although this is really a one large spin system, you can think about it as a collection of spin half particles, and that's the analogy which they use here. It has been used earlier in many theoretical works. So they then look at this as 3 spin half particles and ask for the entanglement of one spin half particle with the other 2. And this is what this is the summary of the results. This is again the Poincare surface of section. What is plotted here are the collective spins coordinates, theta and phi. The spin lies on this these are the azimuthal and polar angles on the spin sphere, so to speak. And the difference between these two cases is this parameter kappa, which is controlling this nonlinearity and the strength of the kick. So for a small value of kappa, 0.5, most of the motion looks regular, whereas at 2.5, this looks like the typical mixed phase space, which I showed you for the Lima zone billiard. And what they do is they prepare initial states such that one can start off from anywhere on this phase space. So you start off with the initial state there, and then you do this kicking protocol for many times. So here they do it for at least 20 steps. And they monitor, so then they do a full state tomography. They see the density matrix, and then they can calculate various things, but they calculate the entanglement between one spin and the other 2. So, so here is the time evolution part of it, but let me just draw your attention to the time average, which is at once giving us some overall picture here. So if we looked at this picture here, kappa is 2.5. Blue means larger entanglement. So this means that if you were to start from a state here and then average the entanglement of one qubit with the other 2, over 20 steps, you get an entanglement which is somewhat less. Whereas in contrast, if you were to start off from this, you get a much smaller entanglement. And they point out that although it's only a 3-qubit system, so it's really only 8-dimensional, there is an unreasonable correlation between such a picture and a classical phase space, which is really obtained in the case of large J. This is the large J limit of the kick-top Hamiltonian. So the claim is that there is a thermalization going on in the sense that for the single qubit, the other 2 qubits are acting like a bath. If the entire initial state is in something where the corresponding classical state is unstable or chaotic. On the other hand, if it's not, it's not as much entangled. There are some features in this, like there are symmetries here, which are not really explained in this. So there are other experiments, like there was a cold atom experiment, I think about 6 years ago at least, which also showed essentially that you could that there was a strong connection between entanglement, a purely quantum quantity, and classical chaos, something which is also peculiar to classical mechanics. So I'm going to just to set the stage, I'm going to recall some of the basic basic notions, or so about entanglement itself. So we have in mind a pure state in this bipartite space. So I and alpha are the orthogonal bases here, and these are some complex numbers here. So if you were to make a matrix out of this set of coefficients, then the reduced density matrix in state of system A is simply the matrix A dagger from here, and it's an n by n matrix. And the state itself is unentangled if and only if these states are pure states. That means that the square of it is itself. Now, I'll be concentrating on these numbers here, which are nothing but the eigenvalues of the reduced density matrices. And the eigenvalues are the same, whether you consider this density matrix or that, because the original state was a pure state. And this also leads to the well-known Schmidt decomposition, which is the most optimal way of writing this bipartite entangled state, potentially entangled state, in terms of a single particle orthogonal basis. So the coefficients, the Schmidt coefficients, are simply the square root of the eigenvalues of the reduced density matrix. And we arrange them so that the lambda 1 is the largest and lambda n is the smallest. And so the lambda I are simply eigenvalues of the reduced density matrix, and sometimes in the condensed matter literature, log of, actually negative log of lambda I is called the entanglement spectrum. It's more jargon really, but okay, we are concerned with the eigenvalues of the reduced density matrix. And the entanglement measure in this pure state is simply the von Neumann entropy of the reduced density matrices. It doesn't matter which reduced density matrix you use, and it's given by the sum here. It's 0 if and only if the state is unentangled, and it's log n if the state is maximally entangled, if and only if the state is maximally entangled, such as a Bell state as an entanglement of log 2. The other entropies which I'll be talking about is Sales entropy, the so-called Sales entropies, which are related to the moments, the other moments of the reduced density matrices. They are related to these eigenvalues through these sums. This alpha can be any real number. As alpha tends towards 1, this entropy reduces to the von Neumann entropy. Alpha is 2 is the linear entropy. So so all that is just the definitions. Now we can ask, we have the entire space of pure bipartite states. Suppose we sample them uniformly from the Hilbert space, then what is the average entanglement which we can expect? So this is a question which can be framed in terms of a problem in random matrices, where we construct this matrix MM dagger. Remember that A dagger is the structure of the reduced density matrix. So MM dagger divided by trace MM dagger, where M has Gaussian random numbers. Then the entropy of this, the average entropy of this ensemble is the average von Neumann entropy, or the average entanglement. So this has remarkably an exact solution. By exact I mean also for finite n and m, and is given by this. But so for instance, for 2 qubits, the average entanglement is 1/3, whereas the maximum is log 2 in this. But for large system sizes, m and n, this is the approximate average entanglement. And if n is equal to m, they are symmetric subspaces. This is log n minus half. Since log n is the maximum possible entanglement, log n minus half appears to be rather small deviation from log n for large n. So one might say that for large dimensional spaces, typical entanglement is almost as large as the maximum possible. And also, if m is viewed as a much larger, is actually much larger than n, and in which case it can be viewed as a reservoir, this tells you that the subsystem is becoming really completely like a completely mixed state, and you have the maximum possible entanglement. namely log n. So this formula has a long history in its derivation. There's an article by Seth Lloyd and Pagels in Annals of Physics in '88 called Complexity and Thermodynamic Depth, where they buried somewhere in the paper the reduced the joint probability distribution of the eigenvalues of this reduced density matrix. Don Page, using Mathematica and arguments from electrodynamics, actually conjectured this formula, which was then proved by Siddharth Sen and others. And there was an earlier work by Lupkin who looked at and actually got exact formulas for the linear entropy much earlier. Okay, so why bother? So as far as random states are concerned, typical states are, aka random states, are somewhat like random numbers in as far as classical computation is concerned. So the generation of random states is an interesting and important important thing to do, not only from the point of view of equilibration or foundations of statistical physics, but also very interesting applications in quantum information protocols, encryption and data hiding, information locking. You can see more of these, especially these two, in the works of Hayden in this paper and in the related papers which are there. So there is a reason to try to generate random states and to make use of them further. So so how do we generate these kind of typical states? Especially starting from states which are not typical. So this is something which is interesting, but I'm going to really talk about just eigenstates of systems. So again, so typical entanglement in quantum chaos. I'm going to really talk about a coupled kick pendulum. So this is a single pendulum. It's a textbook example of a classically chaotic system. This corresponds to this map, which is connecting Q and P between the kicks. And if we iterate this, so this K is now the kicking strength. It's like the kappa, which was there in the kick top. So if K is 0, it's just a free rotor. It's an integrable system. If K is small, like 0.3, sorry, it's in two spaces, it's looking essentially like a pendulum. And as we increase K, you see this transition. At K equal to 7, there's no apparent regularity. There is one connected ergodic component. And it's very simple to quantize such a system because it's a kick protocol there. The flow K operator is simply a product of this kinetic energy and another product which is of the potential energy. So such systems the study of such systems were initiated long ago and have been studied for a long time. So what we're going to talk about, since we're going to be concerned about entanglement, is really coupling two such kick pendulums. So we can consider a Hamiltonian like this. So there are two pendulums, and there's a coupling of cos Q1 plus Q2. So the whole thing is again kicked. So exactly such systems have been studied. In fact, the same system has been studied in other contexts earlier. And there's been a more recent work which looks at very closely this system from a classical as well as some quantum properties. The problem is that it's a higher dimensional maps. Here we could just plot these maps. Here these are 4-dimensional maps with genuinely different classical properties. But we can quantize this map easily. So what we have is a tensor product of the individual standard maps, and that's the coupling. So there are 3 parameters: the individual standard maps, or the individual pendulars amount of chaos or deviation from integrability, and that's the interaction between them. What we do is also make the space compact. Classically, we put periodic boundary conditions are natural in position, but we also put boundary conditions in the the momentum direction so that the phase space becomes a torus. This results in finite dimensional matrices. So it's finite dimensional Hilbert spaces. So each of these subspaces are n-dimensional matrices. So the interaction is n-squared dimensional matrices. And this n is related to effective Planck constant by this, so that the classical limit is also the large n limit. So we'd be interested in the entanglement in the eigenstates of this coupled system. So it's a unitary operator. It has this complete set. And especially we are asking for entanglement as a function of these Ki and B. So this is a very early result where we have plotted the average entanglement in the eigenstates as a function of this coupling B. And one sees that it increases from 0 at zero coupling, of course, and then saturates to a value which depends on the system size n, dimensionality of this. So there are two n by n systems here, and this saturation is exactly log n minus half as which is the random matrix average of the entanglement. And this is across a single spectrum for n equals 40 and an interaction strength of 2. So the interaction strength of 2, but n is 40. So there is most of the states here. So what is plotted here is there are 1,600 states. What is plotted here is the entanglement of them. So most of the states are clustered around this log n minus 2, which is this, log n minus half, which is a solid line. And there are deviations which come because the states are localized. But what we are interested in, and that's really the recent work, is that there's a limit where we seem to be able to say a lot of things analytically, and that is in the limit when all limits are non-integrable. That is, even the non-interacting limits are themselves chaotic. So, for instance, if we take interacting particles in a quantum dot or a billiard, we would rather study the case when the interacting particles are in a stadium, and we claim that that's a more easier thing to at least that's the situation where there is a large entanglement production which seems to be universal, and that's precisely what we are studying. Or one can consider spin chains or ladders, each of the spin chains already in a random phase or an ETH phase. But the model which I just now introduced is what we are going to use to test the theories of, again, coupled kicked rotors, but K1 and K2 large. So what I showed here was K1 and K2 small, just 0.1 and 0.15, which means that the uncoupled systems are not fully chaotic. So K1 and K2 much larger than 5 or so, it's fully chaotic. So, some remarks about these kind of systems is that the non-interacting limit still has Poisson statistics which actually characterize integrable systems. That means that there will be very small level spacings seen in them. That is, resonances can dominate in the small interaction regime. So eigenvalues are like that of an integrable system, but eigenfunctions are randomized. So it's a sort of a peculiar situation that arises here. But in this case, what one sees is that as a function of the interaction, which is expressed through this lambda, which is not just b, but is scaled by the system size n through this n to the power 4b squared. So this is the proper way in which to look at, because this is the dimensionless interaction strength. So this is the effective scaling parameter in this problem. If you looked at it like this, then the von Neumann entropy goes from 0 to the random matrix value along these circles for the eigenfunctions of the standard map. A perturbation theory which we work out is valid here. And there is a sort of an interpolation, and there is a recursive use of perturbation theory which allows us to go beyond this. And so there is really a theory curve here which fits rather well. And this is for the linear entropy. These are for some other entropies of the Salis entropies. But so we seem to have a pretty good handle of what happens to entanglement across a very large range of interactions in this particular case. Yes, so this is where this particular work has been published. So to give some more details of what's going to, so the claim is that actually entanglement in the situation where we have weakly interacting, strongly chaotic systems is universal in the sense that given a system, we will calculate this effective transition parameter, and then the phenomenon entropy is going to grow. Actually, this is not just the phenomenon entropy. This is the Salis entropy, which is parametrized by this alpha, grows at the rate of square root of lambda. So not at lambda, but square root of lambda, which is actually much larger. So this is again coming because the non-interacting systems are fully chaotic. And these coefficients here are interesting numbers which arise in other studies of transitions from localization to delocalization, such as that of Anderson transitions. So, for example, the phenomenon entropy has this kind of universal growth, the linear entropy has this universal growth, and the non-perturbative regime, to a large extent, is described by a simple exponential extension of these. To give more, to give a more detailed picture of what is happening, this is the behavior of the largest eigenvalue of the reduced density matrix. Starts off at 1 and goes to about 4 by n. The second largest eigenvalue, everything else starts from 0. The second largest eigenvalue starts off and goes there. So in the perturbative regime, really in the deep perturbative regime, it's the smallest eigenvalue, it's the largest eigenvalue and the second largest eigenvalue that dominate the scene. And we can do a perturbation theory analysis of this. I'll not go into the details of this, but it's just based on normal textbook perturbation theory, but augmented with some statistical facts which come because the unperturbed systems are chaotic. But not just that, if we try to calculate from naive perturbation theory and using these statistical inputs, we try to calculate, for example, the average second largest eigenvalue, this blows up. So there needs to be a regularization. And the reason for these kind of blow-ups is because of the fact that you have actually resonances, which are coming because the systems are uncoupled to begin with. So there are very close energy level spacings. And in fact, that is what is responsible for the creation of entanglement at this early stage and very, very rapidly. So we have to take into account these resonances by a regularization that has been used before in many, many contexts, I think. And once one does that, one sees that the deviation or the second largest eigenvalue is not proportional to lambda, but in fact square root of lambda. And also, therefore, the deviation of the largest eigenvalue, lambda 1, deviates from 1 by square root of lambda. So, and one can calculate all the, the moments in general, lambda j to the power alpha for alpha greater than half. And there are these, again, these universal coefficients which come. Okay, so I think I'm pretty much out of time. So let me just mention that as far as distributions are concerned, so the distributions of these eigenvalues, lambda 2 and lambda 1, in the perturbative regime, the largest eigenvalue and the second largest eigenvalue have interesting power law tails in them. So this is the distribution of the the second largest eigenvalue, but scaled by this universal transition parameter lambda. It has a distribution which can be calculated using perturbation theory and shows a power law tail. So what we show here is data from the quantum standard map and the perturbation result, and fits very well across this entire regime. And also the distribution of the largest eigenvalue is a sum over many such fat-tailed or heavy-tailed variables, each going as 1 over x to the 3 halves. So a generalized version of the central limit theorem then leads us to this fact that the deviation of the largest eigenvalue from 1, scaled again by this universal transition parameter, is got a universal distribution, which is the Levy distribution, which is one of the stable distributions with a power law tail. So this is, again, comparison of numerics with this result. It's pretty good here. It's not expected to be good here because our results are really valid to order square root of lambda. We don't have results of the order of lambda. So once we turn on so that's all in the perturbative regime. Once the interaction increases, there is a drive, as I said, towards thermalization, if you wish, or complete randomization across in the full product space, and that's what is shown here. But here you see that if suppose you were to look at this, there is a square root of lambda about 2, it's already close to its asymptotic regime. So one would think that at these values of the interaction, the system is thermalized. But if we look more closely at various other quantities, it seems that this is not entirely true. One such quantity is the largest eigenvalue itself and its actual distribution. So the average of the largest eigenvalue starts from 1 and goes to almost 0 and scales as 4 by n for large n. But so we can look at the deviation of the largest eigenvalue from 4 by n and scale it appropriately, because we expect that if things are actually randomized, this will follow the universal distribution of Tracy Widom, which is the extreme value statistics of random matrix theory. And we see that actually when we compare numerics with such a scaled Tracy Widom, that it doesn't fit even at square root of lambda as high as 6 when all these things are thermalized. As high as 10, there are still visible deviations. It's only when there's 14 that it seems to fit the Tracy Widom perfectly. So we conclude that actually thermalization, there are many scales across this. So one of the, so entanglement seems to be governed by a shorter scale, whereas there are other quantities such as this, which would indicate the fact that actually there is a long-term memory of the fact that it started from an uninteracting or non-interacting system of product state. So to summarize, when fully chaotic subsystems start to weakly interact, entanglement production is rapid, analytically calculable, and governed by the same transition parameter as level fluctuations. I didn't talk about level fluctuations, which have a transition from Poisson to Wigner. It's the same transition parameter. This is work which we are currently writing up and which I summarized here as the largest eigenvalue, for instance, in the perturbative regime, as well as actually entropies are heavy-tailed, and lambda 1 in particular is Levy distributed. And it tends towards the, as I said, towards the expected Tracy Widom distribution in a very slow manner. So many open questions coupling integrable systems or intermediate ones. There are very similar transitions seen in many-body systems. For example, many-body localization is one such thing where you go from an area to a volume law. How much of any of these kind of things is valid is clear.
I was wondering what would happen if you consider the more typical situation of where a system that is fully chaotic has the Wigner-Dyson statistics.
No, but the fact that it's Poisson is coming because the systems are not interacting. So each one of them is Wigner, but because it's not interacting, you have the Poisson statistics. So the Poisson statistics is not an unusual thing here.
Sorry, I didn't understand.
Hear you?
This conjecture by Don Page. So I was wondering whether it's also true for eigenstates of integrable systems that this thing holds.
So it's actually interesting that you are getting volume law in these integrable systems. Well, the page conjecture, which is of course not a conjecture, it's a completely proved thing, is simply the average subsystem entropy when the state is uniformly sampled from the entire Hilbert space. So it's not a conjecture. Now whether why this should be, whether this is exactly what is going on in integrable systems is actually not clear to me. I mean, something like this could be happening because you have, for example, in spin systems like in the MBL case where you're in the ETH phase. So it's still valid. Suppose we take L-half systems. In fact, if you would allow me to go ahead, here is the MBL situation, and so this is in this Ising model, and the Ji is the disorder strength. So if this Ji is such that its strength lies somewhere here, this is the average entropy of the eigenstates, and it's very close to log n minus half, which is these dotted lines. So, but you see this entropy now goes as L half log 2. So your volume law basically comes from this L. So what might happen in integrable systems is that the coefficient here might be smaller. It might be still proportional to L and therefore make it a volume law, but the coefficient here might be actually different. I don't know of any random matrix ensembles which have that property, but it might be interesting to try to construct something.
So now, how do you use this random matrix theory to compute the entanglement? Like, I mean, you just think of these two guys as described by two random matrices, and
well, we have two regimes. One is the perturbative regime, and so let me probably go here. Yeah. So the essential inputs into perturbation theory are these off-diagonal matrix elements of the interaction. So if the initial systems, the non-interacting systems, are themselves chaotic, then this matrix elements are exponentially distributed. So this is coming because of the eigenstates are randomized, and then the other input is with these energy differences, which is coming from a Poisson spectrum, although the individual systems are completely chaotic because they are not interacting. So these are the two inputs statistically. So this W, which is essentially this modulus squared, is distributed in an exponential way apart from the scaling B, which is the mean square of diagonal matrix elements in the unperturbed basis. And D is the average, is the mean spacing, unperturbed mean spacing. So, but this S is as if the levels are in a Poisson process. That means that the levels are arriving independently of each other. So that's how the eigenvalues are, which will be the case in an integrable system. So those are really the only two things, and then it's perturbation theory. And so that's why we use this e to the minus w here, which is coming from the randomized eigenstates. And this is a curious thing because, okay, we are looking at lambda 2, which is so we need given n level, which is the closest energy level next to it. And that has this distribution. So it's not e to the minus s in a Poisson spectrum, but it's twice e to the minus 2s. So essentially, that's all that goes on. I mean, you can also have a random matrix model, a complete random matrix model, which also we have studied, where we have that kind of a structure where these two are random COE matrices, and then you have a diagonal matrix here, which is this coupling matrix with e to the I epsilon some x, where x is uniformly distributed. So one can construct random matrix models also, which are universal sort of things. We have actually done this, and I didn't discuss it, but here the triangles are the random matrix models. They have a different lambda. So we have to calculate this lambda for that separately, which is just this off-diagonal matrix element and the mean level spacing. Depends on these two.